Okay, this is our next example then for velocity time graphs. It's a bit more spicy, so we need to concentrate a bit more and see how we get on. Two pieces of information again. You need to know gradient is the acceleration, and the area underneath the graph is the displacement. Man is jogging along a straight road at a constant speed of 4. He passes a friend with a bicycle at t equals 0, so we're going to put our 0 here, who is standing at the side of the road, and 20 seconds later the friend cycles to catch up. The cyclist accelerates uniformly at 3 meters per second squared until he reaches a speed of 12 meters per second. He then maintains a constant speed. On the diagram, sets the velocity time graphs for the jogger and the cyclist. Find the time that elapses before the cyclist reaches the jogger. So we're going to go 0, 2, 4, 6, 8, 10 and 12. You can see I've already started that. Velocity going up the side, time going along the bottom. Under jogger, sorry, I've misplaced my ruler, so I'll go with this. I'll do it nice and thick so you can definitely see it's not just a line. But this is our jogger. They are going at 4, and they go at 4 the whole time. That doesn't change, just for the whole journey. So that's our jogger then going at 4 meters per second the whole time. What about our cyclist? Our cyclist pass it, and then 20 seconds later, the cyclist starts. So I'm going to take this in as 20. Not quite as accurate going along the bottom here, but that's okay. And they speed up 3 meters per second until they reach 12. So I can see 3 meters per second squared until they reach 12. That's going to take 4 seconds because they go at 3 meters per second squared quicker every time. You could use a gradient. The gradient's going to be 3, so every one you go across, you're going up 3. You could think about it that way, but whatever way you want to do it, 3 meters per second is going to take 4 seconds to get there. Hope I said that last time. So at 24, then they're going at 12. So that's the information then that we need, and they're accelerating. That's why it's going like that. And then they go at a constant speed of 12, I think, until they catch each other up, and that's what I have to find. But that's our diagram there. That's part A done for us. On the diagram, sketch the velocity time graphs for the jogger and the cyclist. Find the time that elapses before the cyclist reaches the jogger. So somewhere down here they're going to reach each other, and I'm going to call that time t, and that's when we need to find. Alright, so let's see if we can kind of suss that out. So what's happening at that particular time? So let's do a beautiful diagram here. They're both starting here and they're going this way here. Here's my jogger. Then the cyclist starts 20 seconds later. So here's the jogger going, cyclist starts and tries to catch up. So how far have they travelled? What's important is they've travelled the same distance. So at this time t, they've travelled the same distance. What does that mean? That means that at this time t, the areas underneath their respective graphs must be the same. The area of that must be the same as the area of that, and that's how we're going to work out our value of t. Alright, so let's take a wee look first of all then at the jogger. Displacement is going to be the area of this graph. So that distance there is 4, that distance there is t. So that's easy. It's going to be 4t. This one's a wee bit more messy. Cyclist. So what I'm going to try and work out here, let's do a diagram. We could do it as a trapezium. I'm not going to. I'm going to do it as a triangle and a, what do you call that, a rectangle. Okay, so let's see. The cyclist is going to have travelled this, the area of this plus the area of this. So that's going to be a displacement then of a half times base times height, which is 4 times 12, plus this, we're working out the area of this rectangle. The height is 12, and this distance here is t take away 24. I hope we can see that. That's quite hard to see, but that's the way it'll work out. Let's do some sums. 2 times 12 then is going to be 24, plus 12t minus, I think that's 288, isn't it? If you do 12 times minus 24, and we end up then with that. So how far has the cyclist travelled? They've travelled, we can tidy it up again, can't we? 12t, and then minus 288, we have that minus 264. So the cyclist has travelled 12t minus 264 when catches up. The jogger has travelled 4t when they catch up. So they've both travelled the same distance. So that particular case then, 4t equals 12t minus 264. Nothing too complicated here. This is like a year 8 equation to try and solve. I would take the 4t over to this side, the 264 over to this side. 264 equals 8t, and so time then equals 33 seconds. So it's 33 seconds in until the jogger catches up with the cyclist. Quite tough, but that's the way we can kind of work it out. So what did I do here? Again, I did use this information. The gradient was acceleration. That helped me get this wee line in place here, and then we knew that at that particular time they've travelled the same distance. They both start here. The jogger goes past. 20 seconds later, this guy goes to catch up, and at this stage they've travelled the same distance, you know, kind of from here to here. So we know the areas must be the same, and try and suss out then from there. So quite tough, but that's the way you do questions then like that.